All right, so we're going to get started in section 1.3, and 1.3 is on a topic called vector equations. So remember what we did in 1.2? We used row-reduced echelon forms of augmented matrices to solve systems of linear equations. So now what we're going to do is we are going to look at vector equations. Now, first off, you should ask yourself, well, what's a vector? All right, we know what an equation is, but what's a vector? In this course, we're going to be dealing with column vectors. Okay, so anytime I say the word vector, I'm talking about a column vector. Now, obviously, in other realms, people use rows for vectors, so they'll use row vectors, they'll maybe use some different notations, but in this course, for right now, we're going to use column vectors, all right? We will expand that concept in chapter 4, all right? So, for example, what I mean by a column vector is just a matrix with a single column. So, for instance, we could let u be equal to 5, -2. That would be a column vector. And another vector we could have 3 entries. So this is a 3 by 1 matrix, 3 rows, 1 column, and that would be a vector. Now, notationally, what'll happen is both in the book and on my notes, we denote a vector, we usually boldface those. So if we are denoting some sort of a number, we leave it as not bolded, but when you denote a vector, most of the times in the book, it will take a boldface, unless there's a typo. And the same thing is true for my notes. Unless there's a typo, I'll try to boldface all the vectors. All right, so you can tell that variable is intended to be a vector and not just a number. Okay, now one thing about vectors is obviously the size is important, but also the order is important. So a matrix if we have 2 matrices and they're both 2 by 1 matrices, I can have the same entries, but if those entries are in a different order, then those are not the same vectors. Okay, so for instance, 5, -2 is not the same vector as -2, 5. So order and placement is very important when we're dealing with vectors. Okay, and just a little bit of the language that we use. A vector with n entries, so an n by 1 column matrix, n by 1 matrix, we call that an n-dimensional vector. And the set of all vectors with n dimensions, whose entries are real numbers, is called Rn. All right, so R, which is the symbol for the real numbers, and then we use an exponent to mean we're n-dimensional. So for instance, if A and B are real numbers, then this matrix here with an with a real number in the first row and a real number in the second row is a two-dimensional vector, and we say it is in R2. Okay, so R2 is the set of all vectors with 2 real numbered entries. And also, I might bring up the concept of the zero vector here. Every single Rn contains a zero vector, which we'll denote as just a 0 with a bold, okay? And it's probably what you think it is. The zero vector is just a vector where every entry is 0. So the zero vector in R3 has 3 entries here, here, and here, and they're all 0. Okay, so that's enough about talking about dimensions of vectors. What are we going to do with vectors? Well, first off, we're going to figure out how to do some mathematical operations on vectors. The first one is adding vectors. So if we want to add vectors, we do this entry-wise, okay? Or point-wise, some people say. Entry-wise, point-wise, again, depends on who you're talking to. So we're entry-wise adding. So if I add 4, 2 to 8, -6, I take the first entry in the first row from my first vector, add it to my first entry in the first row of my second vector, and that gives me the resulting entry. So we're going to do 2 plus -6 becomes -4. 4 plus 8 becomes 12. The other operation that we can deal with when we have vectors is called scalar multiplication. So we can add two vectors together and we can do what's called scalar multiplication. Scalar multiplication just means I'm going to take a real number and I'm going to multiply times a vector. So I take a real number like 5 and I multiply times a vector. If you do that, your scalar, your real number, multiplies times both entries. So 5 times 3 -4 is going to be 15 over -20. 5 times 3 is 15. 5 times -4 is -20. So we can add, we can multiply by a real number, and we can put all those types of operations together too if we want. Okay? Now, the standard order of operations is going to apply here as well. You're going to have to multiply before you add, but the point is made. The point's pretty obvious here that you can put scalar multiplication and addition sort of in common and make bigger and bigger and more complex problems like these. So I want you to take just a couple of minutes and try these. I'm going to push, or excuse me, you should push pause on the video and then try to add, subtract these vectors along with the scalar multiplication, and then I'll show you how to do that. All right, so hopefully you went ahead and did that. What I'm going to do is I am going to do that addition right here. Now, what I like to do, you can do this a number of ways. When you multiply the 3 times this first vector, you can create the vector 6, 3. In fact, let me go ahead and do that. So one way to do this is to do all of your multiplication first. Do the 6, 3, and then take that 5, multiply it in. 5 times 0 is 0. 5 times 4 is 20. And then you can go ahead and add it. All right, 6 plus 0 is 6. 3 plus 20 is 23. Okay, so that's one way to do that. Another way you can think about this is notice that when you took 3 times 2, that stayed in this top entry. 5 times 0, that stayed in that top entry. And then we're going to add top entry to top entry. So if you want to decide what the top entry is going to be in this 1, 1 spot, it's going to be 3 times 2 plus 5 times 0. Okay? And you can write in 3 times 2 plus 5 times 0 into your calculator. Calculate that, and obviously that's going to give us a 6. And then for the bottom entry, I can do the similar thing. 3 times 1 plus 5 times 4. And then calculate that entry. And obviously that's a 23, but the point is you can sort of look at and say, well, we're going to be adding all the top entries, and you can do all the top entries all in one step, and then you can do all the second entries all in one step. All right. Or again, if you'd rather take the number times the vector, do all of vector 1 simplification, then do all of vector 2 simplification, and then add them up. Okay. I tend to do the entry-wise one. I think that's a little bit quicker, but it's up to you. So the next thing, the next problem that was on that slide is this one. So I'm going to do this one, 2 times 4. And then notice we have a minus here. That's perfectly okay. Just like the 2 is out here, we distribute the 2 in here. Negative times 3 is a minus 3. So 2 times 4 minus 3 becomes a 5. And then 2 times negative 4 minus a negative 4. So that is negative 8 plus 4. That's negative 4 as that entry. Okay. So that's kind of how to add these things. And the same thing works, or excuse me, it works in the same way if we have 3 entries rather than 2. Okay. So we take negative 2 times 2 plus, notice there's no coefficient here. It's assumed it's a 1 if there's no coefficient, just like any other realm of mathematics. So we take negative 2 times 2 plus 1 times 6, or just 6. My next entry is going to be negative 2 times negative 3 plus 1. And then I'm going to get negative 2 times 1 plus 1 as my last entry. Okay. And I guess I'll do one more step here, see if this will work. So what are we going to get? Negative 4 plus 6 is a 2. That's a positive 6 plus 1 is a 7. Negative 2 plus 1 is a negative 1. Okay, so the vector we get out when we do that calculation, when we do that scalar product and vector addition, is going to be 2, 7, and negative 1. Now, one thing that you'll notice really quickly is that all of these vectors matched up in size. If somebody were to ask you to calculate this, a 2-dimensional vector added to a 3-dimensional vector, well, that's actually impossible. So this sum does not exist. Okay, so in order to add vectors up, they do need to be the same dimension. They need to have the same number of entries. Okay, so a 2-dimensional vector plus a 3-dimensional vector is not going to be able to add up. Can't add that one. They can't add those two together. Now let's think of when we deal with these operations of vector addition and scalar multiplication, it turns out a lot of the properties that we're going to be using are going to be properties from the real numbers, because really adding vectors is just adding different entries of real numbers, right? And so when we add 2 vectors, a lot of the properties of real numbers are going to scale over. For instance, when you add 2 vectors, we're going to note that vector addition is commutative. So the order you added them doesn't matter. And also, vector addition is going to be associative. Most of you would have done that naturally anyways, but that's what I wanted to mention that just because, yes, we are doing a lot of the same, excuse me, yes, a lot of the same properties are carrying over from the real numbers. Also, if you think about the zero vector, well, adding the zero vector to anything is just going to keep it the same. All right. So adding a zero vector just adds zero to your entries, so your entries don't change. And then there's also, for each vector, we can find the negative of that vector, or in other words, the opposite when we add. So this is the additive opposite, which means just take the opposite entries. If you have 1, 2, 3, the opposite entries are going to be -1, -2, -3. So we can, for any vector, we can find the negative or the opposite of that vector. Now, when we throw in scalar multiplication, well, we need to know how scalar multiplication works with vector addition. And basically, just like when real numbers, we have this distributive property, well, when we have vector addition and scalar multiplications, well, those also have distributive properties. So if I was going to add two vectors up and then multiply by a scalar, it would be the same thing as multiplying the first one by a scalar and the second one by a scalar. Now, I wrote this down in a way I switched the order, but remember, it doesn't matter if we switch the order because vector addition is commutative. Here, if we're adding scalars and then multiplying by a vector, I could have multiplied that vector times each of the scalars. And then if I have a scalar multiplication times a scalar multiplication times a vector, it doesn't matter what order I did that in. So we have associativity of multiplication, but you have to be a little bit careful here because when I say associativity of multiplication, I'm saying two scalars and a vector. Now I know what you're going to ask, and I'll get to that in just a moment. But for the last point that I want to make, just to notify you of properties of vectors times scalars. If you multiply 1 times any vector, you get that vector back. So 1 times anything is itself. All right. Now, I'm going to state this. Notice we had two scalars and one vector. I said, I know what you're going to ask. You're going to ask, what's going to happen if you have two vectors? Well, as of right now, we are not going to be multiplying vectors. It turns out that multiplying vectors, you can do so in a number of ways. And so there are some ways that we're going to see how to multiply, but that'll come later in the class. But it's not you don't want to entry-wise multiply because that'll kind of screw things up for what we want to accomplish with these vectors. All right, so we do not have a vector times a vector multiplication as of yet. All right, just wanted to point that out. Now, if I have a bunch of vectors, I can take scalars times those vectors and then add up the result of taking scalars times those vectors. That sum will be a new vector, obviously, and that new vector we call a linear combination of my starting vectors. So y is a linear combination of my vectors v1 through vn if y can be written as just scalar multiples plus, excuse me, scalar multiples times each of the vectors all added up. All right. It's obviously called a linear combination because we don't allow any exponents on any vectors. That doesn't make any sense. So this is a linear equation. So we're talking about linear combination. All right, linear combinations are going to be essential not only in this section, but moving forward in all of the entire book, basically. So make sure we understand what a linear combination is. A linear combination is any sort of sum of vectors where I throw in scalar multiplications. Let me explain that by the examples we just did. All right. Excuse me. So we saw that 2 times this vector minus this vector becomes 5, negative 4. So we could say that 5, negative 4 is a linear combination of this vector and this vector. Similarly, we could say that 6, 23 is a combination of that vector and that vector, is a linear combination of 2, 1 and 0, 4. All right? And one of the things we like to do is determine if a vector can be written as a linear combination of other vectors. So here is a typical problem that you're going to see in section 1.3. It's going to say, is the vector B a linear combination of V1 and V2? Now, the answer to this depends on the values of V1, the values of V2, and the values of B. Okay? But we need to find a systematic way of answering this question. And so we're going to do that through this example here. So let's check that out. Let me explain what that is. I'll go back to the Word document here. Okay? So we have these two vectors, and we want to figure out if there are coefficients we can use, if we can write B as a linear combination of V1 and V2. Now, just stating that as what we said is, are there going to be a C1 and a C2 constant real numbers that I can multiply, where I can multiply one constant by V1 and another constant by V2 and get B. All right? Let me make those bold. Okay. So the question is, do these C1 and C2s exist? Actually, instead of using the letter C, because these are actually variables, let me use the letters x1 and x2. All right, so are there numbers that I can plug in for x1 and x2 that make this equation true? Let's write that out. What does that mean? Is B a linear combination? Hopefully you're not thrown off, by the way. I've just kind of said B is a linear combination if B can be written as a sum of constants times V1 plus constants times V2. I just put the B on the right-hand side now instead of the left-hand side. Hopefully you're not thrown off by that. There is a reason I'm doing that though. All right, so let's take that equation and just decide what the V is. So we know what the V's are. The V is that vector. So the V1 is that vector. V2 is that vector. And B is that vector. Okay? So in other words, it's a linear combination. If we can find x1s and x2s that satisfy this equation. Now, what did we just do? We said, well, we know how to add two vectors together. How would I add these vectors on the left-hand side? Well, if I were to add these vectors on the left-hand side, what I'm going to get, hopefully I can do this. Well, x1 times 3 plus x2 times negative 2 is going to be the top entry on the left-hand side. We can write that as 3x1 minus 2x2. The second entry, 4 times x1 plus 5 times x2. The third entry is going to be x1 times 6, or 6x1, plus x2 times negative 3, or minus 3x2. All right? So the left-hand side, we're saying, has to be equal to this, and the right-hand side obviously has to be equal to that. Now remember, order is important. So the first entry over here, if these two vectors are equal, because order is important, the first entry over here has to match up with the first entry over there, which basically is giving me a single linear equation, specifically that 3x1 minus 2x2 has to be equal to negative 4. So my first row gives me a linear equation in two variables. My second row gives me another linear equation in two variables. 4x1 plus 5x2 equals 13. And my last row gives me another linear equation in two variables. So another way to ask that same problem is to ask, is this system of linear equations consistent? Can I find a solution for that? And so what I would do if you're looking for a solution to this system of linear equations is go plug it into your calculator. Oops, it's taken me a second. Sorry about that. So go plug this into your calculator and see if the augmented matrix has a solution or if it doesn't have a solution based on row reducing the augmented matrix. Okay, so I'm going to do that right now, hopefully. I got to remember what my numbers are. I just wrote my numbers down. I go to my calculator. Again, second matrix. We can edit some matrix. Let's edit matrix A. The matrix that I need, it's going to be a 3 by 3 matrix. So 3 by 3. And then it goes 3, negative 2, negative 4, that's the first row. 4, 5, 13 is the second row. And 6, negative 3, 9 is the last row. So there's the matrix, my augmented matrix. So now we can do our basic thing again where we go into our matrix menu. Row reduce echelon form, that matrix. And all of a sudden I get this. All right. Now, remember what that meant. We did this last time. If this is an augmented matrix, that last row is telling me 0 equals 1. All right? So that last row is equivalent when I row reduce that to the 0 is equal to 1, which means there was no solution. All right? So there's no solution to this system of linear equations, which means there's absolutely no way I could have written B as a linear combination of vectors v1 and v2. So the way we would say that is we would say that, oops, excuse me about, we would say that B is not a linear combination of v1 and v2. Okay? So there you go. Okay? If we could have found a solution, regardless of what that solution was, if we could have found at least one solution, then it would have been a linear combination because there would have been a way to write out or to get those coefficients. All right? So that's what we're dealing with there. One thing I want to mention here is that notice what we did here when we wrote linear combinations. We wrote an equation, a linear equation, where I had vectors in here. That type of equation is called a vector equation, okay? So a vector equation is just simply an equation with vectors. And we're always going to write linear vector equations here. So a vector equation is simply just an equation that has vectors in it, okay? And notice what we did. That vector equation is actually equivalent. Let me step back. Finding a solution to that vector equation was equivalent to finding a solution to a linear system of equations. So a vector equation is equivalent to a system of equations, which is equivalent to an augmented matrix. So whenever we're finding solutions to vector equations, we can do so in the same way we did in section 1.2. That is, put an augmented or associate an augmented matrix with it, and then put that augmented matrix in row reduced echelon form. Okay? So let's go ahead and kind of go back and forth between vector equations and linear equations. Okay? Or I should say vector equations and systems of linear equations and augmented matrices. I want you to take a minute and think through how this system of linear equations could be written as a vector equation. All right, hopefully you did that. If you didn't push pause, do so now because I'm going to show the answer. All right, so the first thing we have to notice is how many different variables we have. Notice we have an x1, an x2, and an x3. So when we create our vector equation, I'm going to end up with an x1 as the coefficient times a vector, and then an x2 as the coefficient times a vector, and an x3, oops, as the coefficient of another vector. And then we're going to have that equaling some sort of constant vectors. okay? Then all we have to do is say, well, each variable gave me a column. Each equation is going to determine one single row. All right? And since we have three equations, we're going to end up with 3 rows. That means each of my vectors has to be 3 dimensions. And by the way, if one of them's 3 dimensions, you can't have another one that's going to be 2 dimensions. Hopefully that makes sense. So here's what we do. We say, okay, first equation is 3 times x1. So we put a 3 so we can times it by x1 plus 5 times x2, 5 times x2 minus 7 times x3, we'll put a minus 7 there, is equal to 10. All right? So you can do that row-wise. Once you get good at this, what you're going to figure out is you're going to say, oh, these are just the coefficients of the x1s. 3 is the coefficient of x1 in row 1. In row 2, equation number 2 here, the coefficient of x1 is just a 0. All right, there's no x1 here, so we just put a 0 there. 0 times x1, don't have to write anything. 6 times x2, 9 times x3 equals 17. Then that last equation, 4 times x1 minus x2, so negative 1 times x2. There's no x3 here, so we put a 0 x3 is equal to negative 11. All right? So if we were to rewrite this equation as a vector equation, this is how we would do it. Okay? Now, one thing I do want to mention before I move on, that vector equation right there, these x1s and x2s and x3s are just constant numbers. So it actually does not matter whether you put them in front of your vector as your scalar multiplication or behind your vector as your scalar multiplication. So the book tends to put the the real number in front of the vector. Some people like to put the vector in front of the real number. It gives you the same answer either way. All right. So that's how to take a system of linear equations and translate it into a vector equation. Now, we're going to go the opposite way next. I want you to take this vector equation. I've put the x1, x2, x3 after the vectors. So take that vector equation and translate it into a system of linear equations, and then go ahead and get the augmented matrix that's associated with this vector equation. Push pause on the video and try that. All right, hopefully you did that. Whoops. So go back to our Word document here. We wanted to take this vector equation, write it as a system of linear equations, and then translate it into an augmented matrix, excuse me. So as a linear equation, 6x1 minus 2x2 plus 1x3 equals 12. That's my first linear equation. My second linear equation that I'm going to get is 3x1 plus 4x2 plus 1x3 is equaling 4. All right, so there's my system of linear equations. If I want to create an augmented matrix, well, what do? Let's do, oops, I apologize. Let's do that. And then another one of those. Sorry. We're going to need 4 columns. Hopefully you see that. All right. To get an augmented matrix, we're going to end up with 4 columns. And those columns, well, the first column will be the coefficients of the x1, 6, and 3. Second column will be the coefficients of the x2, -2 and 4. Coefficients of the x3 are going to be the third column. And then, obviously, if you wanted to, you could draw a vertical line here for where the equal signs are at. But my last column is going to be a 12, 4. All right. So there's the augmented matrix that corresponds to this vector equation. Now, once you've done this enough, you'll be able to jump right from the vector equation to the augmented matrix. Because notice again, we're talking about columns. All these columns are just the vectors that we see up there. Okay, and I do it in order where, again, we have x1 as represents our first column, x2, coefficients of x2 are represented in our second column, and so on and so forth. So I want you to try one more of those. This time, I've written the x1 and the x2 in front of the vectors. And this time, I want you to just write down the augmented matrix without having to write down the system of linear equations. In other words, don't write down that middle step. All right, hopefully you've done that. Push pause on the video if you haven't. Go back here. So we have that system, or excuse me, that vector equation. If you're going to create an augmented matrix, it's going to have 4, 7 as the first column, -8, 17 as the second column, and 1, 0 as the last column. There you go. That's the augmented matrix we'd use. Okay. And so if I ask you to solve this for and find x1 and x2, we could solve this by row reducing that augmented matrix right there. One more concept that is closely related to linear combinations is the idea of span. Okay? So, excuse me. So the span of a set of vectors is the set of all linear combinations of those vectors. Okay? So the span of 4, 7, and 1, 3 are all the vectors that can be written like this, where C1 and C2 are, oops, that is a typo. I apologize for that. C1 and C2 are not vectors, they are just real numbers. Okay? My bad. So the span of a set of vectors is the set of all things that are linear combinations. So if we go back, this B was not a linear combination of V1 and V2. So this B would not have been in the span. Does that make sense? Hopefully. So we saw that B is not a linear combination, so this B is not in the span. But there are a lot of other vectors that would be in the span. For instance, 3, 4, 6 as a vector is in the span because I can put a 1 as a coefficient of V1 and a 0 as a coefficient of V2, add them together and you get 3, 4, 6. So there's going to be a lot of vectors in the span. In fact, there's going to be infinitely many vectors in the span of any set of vectors, so long as we don't have just the 0 vector there. So the span of a set of vectors is going to be a big group of vectors. And so a typical problem would be to ask this: is B in the span of V1 and V2? Now, this is actually the exact same conceptually. They're different vectors, but conceptually, this is the same as asking, is B in the is B a linear combination of V1 and V2? So the span is all linear combinations. So in the span means B is a linear combination of V1 and V2. I want you to push pause on the video and utilize the vector equation and augmented matrices to determine if B is in the span of V1 and V2. All right, so hopefully you did that. It might take a minute to, again, do all the things and put it all together. But once you get the hang of it, it's going to be a pretty straightforward process. And being able to utilize your calculator cuts down on the time, like I said last time, by like 2,000 hours in this course, because using that row reduced echelon form function on the calculator is just extremely handy. All right, so what you would do is you would take those vectors and you'd say, well, is B in the span? That means, is B a linear combination? So if B is a linear combination, then I can write out this vector equation and find a solution for x1 and x2. Well, that vector equation is going to have the same solutions as some system of linear equations, which is going to be associated with this augmented matrix. Okay, so we write vector 1, vector 2, and then the B, V1, V2, B. Now, with this matrix, we're going to put this matrix into row reduced echelon form. When you do that, you end up with this. Now, be careful here. We have two variables only. This third line was our constants. So what that last line there is telling me is that 0 equals 1, which is a no solution case. That means there's no way to find x1s and x2s to make this work, which means that B is not in the span. So, oops, B is not in the span of V1 and V2. Keep doing that. All right. So the no solution case, that 0 equals 1 on that last row, tells me that B is not in the span. I should make those bolded so that they do represent vectors. All right, let's try one more of those. We did this, is B in the span of V1 and V2? I want you to determine if this B is in the span of V1 and V2. All right, so hopefully you push pause on the video and did that. If you haven't yet, go ahead and do it. Now you'll notice the V1 and the V2 actually have not changed from the last problem. So there's nothing earth-shattering about this. All we're going to do is do a very similar thing to what we did last time. In fact, it's so similar, I'm just going to go back up here and change the numbers. 0, 2, negative 14 was my new B. So 0, 2, negative 14. If B is a linear combination, then sum x1 times my first vector plus sum x2 times my second vector is going to have to be equal to 0, 2, and negative 14. In order to solve that vector equation, I'm going to create the associated augmented matrix and then row reduce it. The associated augmented matrix is going to be just like my old one, but now in that third column, it'll be 0, 2, negative 14. And when you row reduce echelon form this one, what you'll find is that you end up getting the following matrix. 1, 0, 6, 0, 1, 4, 0, 0, 0. Now remember what these columns and what these rows represented. They represent the rows and the rows of an augmented matrix, which are coming from a certain equation, and those equations have coefficients of x1 are going to be in our first column, coefficients of x2 are going to be in our second column, and our constants are going to be in our third column. So what this means is that x1 would have had to have been 6, and x2 would have had to have been 4. So we found one solution. It's a unique solution, meaning there's no other, it's not an infinite number of solutions, but there is this one solution. Since solution exists, that means this B is a linear combination of these two vectors. So B is a linear combination of the two vectors because we could find a solution. And another way to write that is B is in the span of those two vectors. All right, so you can write it either way. They mean the same thing. B is a linear combination of those two, or B is in the span. All right, I want you to try one more. Oops, I'm sorry. One more version of this. The other version of asking the same question is just asking the same question, but instead of having our vectors separated out, we ask ourselves, is B a linear combination of the columns of A. So I view the columns of A as three separate vectors. Is B a linear combination of those three vectors? Or, identically, you could say, is B in the span of those three vectors? Go ahead and push pause and try to determine if B is in the span of those three vectors. All right, so let's go ahead and solve this problem. We'll notice something really quickly about this, and we'll eventually skip steps, but I'll write all the steps in the first go round. Okay. So I want to figure out if this B can be written as a linear combination of these columns from A. Okay. That's equivalent to saying, can I solve this vector equation? X1 times the first vector plus X2 times the second vector plus X3 times the third vector is equal to B. Okay. And we've seen that basically what that's going to do is that's going to force us to row reduce echelon form this big matrix. Now, once you've seen this once, what you'll notice is that this augmented matrix that you're trying to row reduce is basically just the first 3 by 3 component of that is identical to your matrix A, and the last column is identical to your matrix B. So when you're actually doing this on the homework, you're probably going to skip this second step. You don't have to write it as a vector equation every time because you know that the augmented matrix is just going to be a 3 by 4 matrix where it's the matrix A and then I add on that column of B at the end. And by the way, when I did go ahead and row reduce that augmented matrix, I got really kind of some nasty decimals there. My first row came out to 1, 0, 0, and then negative 50 over 149. My second row came out to 0, 1, 0, and then 28 over 149. Oh, this is not going to be a nice looking matrix. And then my third row came out to be 0, 0, 0, 1. And then 4 over 139. Or 149. I apologize. Okay. So I got this matrix. Now it's not scaling very nicely. Maybe if I make these fractions a little bit smaller, let's make those 12 points instead, or 12 point fonts. Yeah, that didn't help either. So we'll undo that. The short of the story is this. X1 is equal to negative 50 over 149. X2 is equal to 28 over 149. And X3 is equal to 4 over 149. Okay, so that's my solution. That I do find a solution. So because I found a solution, what we know is that B is a linear combination of, well, in this case, we weren't given specific vectors of, we would say, the columns of A. All right. Or B is in the span of the columns of A. Okay, again, B is a linear combination or B is in the span. Hopefully that all made sense. We came up with some ugly decimals. Sometimes that's going to happen. Sometimes we're going to get ugly looking decimals and things aren't going to come out real nice. But in the end, all that really mattered was that yes, we could find an answer. It was an ugly answer, but we could find an answer, and therefore B is a linear combination of the vectors which form the columns of A. I want you to try this one on your own. Figure out if B is in the span of the vectors formed by the columns of A. Now I've kept the same B, but I've changed up my matrix A here. So see if you can figure out if B is in the span of those vectors. Push pause on the video. Hopefully you've went ahead and done that. If you haven't, make sure you did. All right, so we're going to take our A and our B. I'll go back to the Word document here. It's always nice to just copy and paste. A lot of times, sometimes matrices are bolded. Other times matrices just have just a capital letter to denote them. I didn't mention that, but you'll see oftentimes it's either a capital letter or a bolded capital letter to represent a matrix. Vectors in our book are always going to be bolded. I'm going to, again, try to do that on all the notes. Sometimes I make a mistake, but that's how it works. All right, so in this case, we want to figure out if B is a linear combination of the columns of A. All I'm going to do is I'm going to start by just taking that augmented matrix. The augmented matrix that I'm going to need is 1, -3, 0, 0. Then I'm going to need -2, 10, 8, 2. Then I'm going to need -3, 6, -6, 0. All right. So again, I can kind of skip the middle step. I know what that's going to be. That's just going to be a vector equation with these vectors with some unknowns equaling B. So I can just put in these vectors for my first 3 columns and then this last vector for my 4th column. I'll row reduce echelon form that. When you do, the matrix that I got was not the one I have here. Let me add in a column there at the end. I got the matrix 1, 0, 6, 0. Then 0, 1, 2, 0. And then 0, 0, 0, 1. That last row is the no solution case. So since I don't have any solution, means I can't find a way to make a linear combination of B out of these 3 vectors. So there's no way that you can get B from a linear combination of those 3 vectors. And therefore B, whoops, I forgot to erase that, all these lines. B is not a linear combination of the columns of A, and B is not in the span of the columns of A. All right? So in lesson, in this section, remember all the things that we went over. Okay, first off, We know what a vector is. Then we can add vectors. We can multiply vectors by a real number. We can kind of do combinations of those things, multiplying vectors by real numbers and adding the vectors. That led us to look at linear combinations. Linear combinations created essentially a vector equation that we could solve. So if we ever asked, is y a linear combination of these guys? It's a question of solving and finding coefficients. You can use c's or x's. We've been using x's mostly as our variables. That vector equation, linear combinations of vectors, if I look at the entire set of all linear combinations, that's the span of those vectors. So linear combinations and spans are very much intertwined. The span is the set of all linear combinations. And so we can ask roughly the same question in a lot of ways. Is B in the span? Is B a linear combination of two vectors? Is B in the span? Or is B a linear combination of vectors from a matrix? So that's what this 1.3 is all about. Okay? Next time we'll get into 1.4 and we're going to look at yet one more different type of ways that we can associate vectors and matrices back to our system of linear equations. All right, so that's what's coming up next.